Now, the next review that is relevant in the course of studying stochastic processes is going to be on random variables, okay? So by the close of this tutorial, you should be able to define random variables and identify the types of random variables. Secondly, you should be able to identify the types of probability distributions, and also you should be able to describe a cumulative distribution function. The next thing is that you should be able to identify some numerical summaries for random variables. And the last but not the least is that we should be able to define moment and moment generating functions. Okay, so there will be some examples as well as exercise or trial work in some of these sessions. So now let's jump into the first session. It is going to be on random variables. Okay, so what is a random variable? A random variable x, okay, is a function that assigns a real number to each element in a sample space of a random experiment. So mathematically, we can define a random variable in this form as a function that is going to pick elements from the sample space and maps it to the set of real numbers, okay? Let's take an example. Consider the experiment of testing two electronic components such that when an electronic component is tested, it is either defective with the notation D or non-defective with the notation M, okay? So the sample space of this experiment may be written as shown below. So we can have the two components to be non-defective, or we can have the first component to be defective and the second component may be non-defective, or we can have the first component to be non-defective and the second component may be defective, or we can have both components to be defective, okay? So let X denote the number of electronic components which are defective. So this X will now be a random variable because now it will assign real numbers to each element that we have in a sample space here. Okay, so let's take an example of how this can be done. So we have our sample space here, and we also have the set of real numbers on the other side. And we have our random variable here, which is going to be a function of pick elements from the sample space. This omega yes is a notation for elements from the sample space, okay? Now this random variable is going to be a function, okay? We know a function is a rule or a map that takes an input from a specific set called the domain and produces an output from another set called a codomain. So this will be a codomain, okay? In other words, we can say that a function maps elements from the domain set to elements in the codomain with a property that each input is mapped exactly to one output, okay? So we can have one-to-one relation, or we can have many-to-one relation, okay? But we can't have many-to-many or one-to-many relations, okay? All right, so now let's take a look at the first element in our sample space, which is two components which are non-defective. So once we input this here, this is like a machine, okay? The random variable is like a machine. It has been designed to give us components which are defective, okay? So we're just going to count the number of components which are defective. So once we try to replace this with that, okay, let's see the output. We have 0 here, okay? Which means that it was not able, the machine couldn't detect any defective component in this element. That's why we have the output to be 0, okay? Let's take a look at the second element. Once we try to input this here, or we replace this here, let's take a look at the output. We have 1, okay? So in here, it has been able to detect one defective component. That's why we have the output to be 1. Let's take a look at the second element. Once we try to input or replace this inside this machine, let's take a look at the output. It has given us 1 output. Okay, the output is 1 because it has been able to detect one defective component. The last element is this. Once we try to replace it inside this or place it inside this machine, let's take a look at the output. We have 2, which means that it has been able to detect 2 defective components, okay? So this is going to be the possible values for the random variables, for the random variable x that we have here, okay? Now, because this review is a preliminary course to stochastic processes, let me try and chip in this. Now, in here, we are just trying to observe the number of electronic components at any point in time, okay? Now, in the case where we are interested in the number of electronic components, let's say per hour, or we are interested in the number of electronic components for, let's say, each month, then this will be classified as a stochastic process. Okay, so a stochastic process is just a family or a collection of random variables indexed by a parameter space known as time. Okay, so here, because we want to observe the number of electronic components for each month, there will be a typing component here. So I can just replace it. I can just bring comma and I'll put T here inside the bracket that I have here. Okay, or I can index the time here. Okay, I wouldn't go deep into this because we'll come to stochastic process, but I just want to give you a gist of what stochastic process is all about. Okay, all right, so now let's jump into the next slide, which is going to be on the types of random variables. Okay, so when we talk of the types of random variables, how many types do we have? We have two types. The first one is discrete random variable. What is a discrete random variable? A random variable x is said to be discrete if it can assume a finite number or countably infinite possible values of x. So for example, the number of errors that a machine makes in an assembly operation, the number of customers are waiting to be served at the supermarket, the number of accidents occurring at an intersection a period of time, the number of errors detected in accounting records. Okay, so you can see that there's something common in this example. We have the number of errors, the number of customers, the number of accidents, the number of errors. Okay, so you can see that all this can be counted. Okay, so we can say that discrete random variables often represent count data because you can see that the outcome for this experiment can be counted. So we can say discrete random variables often will represent count data. Okay, let's take a look at the next type of random variable known as the continuous random variable. What is a continuous random variable? So a random variable y is said to be continuous if it can assume infinitely many values within an interval of real numbers. So for example, the length of time to complete an operation in a manufacturing plant, the height or weight of a group of people, the length of lifespan of an electronic bulb or of an electric bulb, the amount of sugar in a bottled drink. Okay, I can also say that the outcome for these examples will assume values within an interval of real numbers. Okay, so we can also say that continuous random variables will often represent measured data. Okay, now let's take a look at this remark. Random variables are denoted by uppercase letters such as x, y, and z, and the corresponding lowercase letters x, y, and z are used to denote the particular values of x, y, and z. Okay, we can have other uppercase letters as well. Okay, we refer to the set of possible values of the random variable as the range. Okay, so let me quickly show you this. So this will be the range. These are the possible values of the random variable. This is looking at the number of electronic components which are defective. So these possible values becomes the range. Okay, 0, 1, and 2. Now, as I have already indicated, that continuous random variables represent measured data, whereas discrete random variables often represent count data. Okay, so this will bring us to the end of this session. I hope you join me in the next video on probability distributions. Don't forget to subscribe if you have not, and thank you for watching.